Thank you. Let me go ahead and welcome all of you to the week 6 of this Frontier in Mechanical Engineering series. I'm welcoming on the behalf of my organizing team. It has been really great to see such a great attendance over the last 6 weeks. And I'm sure we're going to have a very exciting talk from the two rising stars in combustion today. So before we go in that, let me just prime you for the next week. Our next week theme, week 7, is biorobotics. The two speakers are from Penn State, Jean-Michel Mongiu, and from University of Minnesota, Suhasa Kondar Maria. And Suhasa was a graduate from Georgia Tech, so just for the connection. And it will be moderated by Christy Morganson. She is currently Professor and Chair of University of Washington Aeronautics and Astronautics Department. With that, let me bring it today. Our discussion today will be moderated by Professor Tim Lieuwen. Theme is combustion. And I'll go ahead and introduce Tim, and he will introduce the other speaker and briefly talk about the outstanding challenges in the field, and then the floor will be open to both Chris and Mitchell. Couple of housekeeping. If you're not the speaker, once the speakers start to talk, keep your mic muted, and also sometimes it's worth to make sure your video is muted, because then a lot of people on the bandwidth, it should not be a problem. Speakers can keep their mic and video on. Absolutely. The Q&As will be taken at the end of both the speakers finishing their seminars. So hold on, and you can write your questions in the chat. We do have unofficial of happy hour at 4:30, so it will be open. We'll keep it on till 5 if you want to interact with the speaker more. With that, let me go ahead and introduce Professor Tim Lieuwen. Professor Lieuwen is David S. Lewis Jr. Chair, and as well as Executive Director of our Strategic Energy Institute at Georgia Tech. He's an authoritative figure in the area of combustion. He has published books like Unsteady Combustor Physics, and he's a member of a different society. I'll not go through a long thing here, but he's a member of National Academy of Engineering. He's a fellow of ASME, and I'll just say and say Tim was also elected fellow of APS this year, so I'd like to congratulate him for that. More than that, I would like to say why I was really interested to have Tim as a moderator, because he has been a pioneer in helping junior faculty like me really work through the system, try to help them, and look at different area of research. He is a great mentor for people in the community, and with that, Tim, the floor is all yours.
Well, thank you, Devesh, and it's a real privilege for me to moderate this session with two such exciting speakers. Devesh asked me just to say a couple quick things about combustion as a field for those of you who don't work in it, but all I can say is I've been doing combustion research for about 20 years. I've loved every minute of it. It's a lot of fun, and what I think is so interesting about the combustion field is the way it spans, going from basic science, really interesting, very fundamental problems, to hardcore application. Even people who do experiments and never get out of a lab, just the combination of just the multidisciplinary way in which you have to span disciplines of fluid mechanics and kinetics and heat transfer and lasers and optics and things like that. Some of you may know a former PhD student of mine, Professor Jacqueline O'Connor. She's a professor at Penn State, and she always liked to say that the first thing she learned when she worked with me at Georgia Tech was how to weld, and the second thing she learned was nonlinear optics. And so I think that nicely covers the bridge. You know, we're talking here today about rockets and large-scale wildfires or aircraft engines. We're talking about enormous pressures and temperatures, the challenges of making measurements or just figuring out what's going on inside of these systems. And then on the other end, just really interesting applications around just basics of fluid mechanics and interactions of density gradients and shocks and baroclinic torque with fluid mechanics or combustion science. So that's my intro. That's my why this is such a fun field, such an interesting field. And what I'm going to do now is introduce both speakers at the same time, and then I will turn it over to them to each give their 25-minute talk. So I will start with Professor Chris Goldenstein, who is an assistant professor at Purdue. He's an assistant professor of mechanical engineering at Purdue. And he actually received his BS from University of Michigan in 2009, and he worked at Stanford, got his PhD in Stanford in 2014. And since joining Purdue in 2016, he's received a very impressive list of projects and awards. He's received Young Investigator Awards from DITRA, from AFOSR, the INICEP Career Award, and he's also received a NASA Early Career Faculty Award. He'll talk a little bit about his work, about one specific or a set of specific projects, but his research group focuses on development and application of laser diagnostics for combustion nonlinear equilibrium gases. The other speaker is Professor Mitchell Spearrin, who is an assistant professor at UCLA, where he directs the laser spectroscopy and gas dynamic lab, as well as the Mojave propulsion test facility. He has also received a very nice set of early career awards from the National Science Foundation, from the Air Force Office of Scientific Research, the American Chemical Society, as well as from NASA. And his work spans fundamental spectroscopic studies of collisional and radiative processes. He does a variety of different work in optical diagnostics and experimental investigations of very complex combustor facilities. So with that, I will turn it over to Chris to take it away.
All right. How did I just lost the web. There we go. I'm going to share my screen here again. And okay. Okay, so can you see this screen and my mouse?
Yes. Go ahead, Chris.
Okay, well, great. Thanks for the introduction, Tim. As Tim alluded to, I'm going to talk about some advancements in laser absorption diagnostics that we've developed for studying combustion of energetic materials, but combustion more generally. And I'd like to take a moment to also say how much fun this is, and I couldn't agree with Tim more on his thoughts on the field. And this is particularly fun for Mitchell and I, since we're really good colleagues and friends dating back to our time in Ron Hansen's lab. So since I'm going first, I thought I would take a moment to introduce my research and the frontiers of our field before getting into more of a technical talk surrounding these two diagnostics. I'll also introduce you to this field of energetic materials combustion, some of the diagnostic needs that that field is facing, the bare bones basics of absorption spectroscopy, and get into the design and application of these two different high bandwidth diagnostics we've been developing recently, and they're very different. So I thought it was nice to compare and contrast these two together. One uses telecom grade diode lasers and wavelength modulation spectroscopy, and the other uses a ultra-fast femtosecond light source. So, all right. So this is the kind of stuff that I show students when I'm recruiting them. Our mission is to advance the thermal sciences, energy propulsion defense applications through laser diagnostics, and we use anything from diode lasers up to the size of about a quarter, to now this ultra-fast light source that takes up the bulk of an optical table. And while this in and of itself is an incredibly rich field to develop these tools and study the fundamental light-matter interactions, what really pushes us is getting to the point where we can study these combustion applications. And both Mitchell and myself actually kind of cut our teeth working on developing diagnostics for real propulsion systems, whether they be scramjets and pulse detonation engines, to more recently rotating detonations that we've both been studying, trying to make really high-speed megahertz rate measurements in the annulus of these exotic combustors. Since I've come to Purdue, I've started working heavily looking at characterization of combustion of energetic materials. And so we've been studying propellant flames quite a bit, everything from APH-TBB to nano-aluminum composite propellants and even HMX. And the idea is to measure temperature in as many species, quite honestly, as we can, because each species tells us a unique story about the combustion process. We've also used similar diagnostics to study explosive fireballs, which I'll talk about later. And heading forward, we're going to be looking at non-equilibrium kinetics in some very high Mach number shock environments. So that's kind of some of the things we work on. Of course, there's many other applications that we like as well. But I thought I'd take a moment now to talk about the frontiers of our space. We're always trying to make faster measurements, resolve timescales down to microseconds and even picoseconds in some cases. So that's really what my talk is going to get at. And then we also, of course, are interested in making multidimensional measurements. And in the case of laser absorption, that's kind of been its Achilles heel, but we've been making progress on that. Mitchell's going to be talking about getting up to 3D measurements right after me. And then, of course, we always want to measure more and more species, as I just said, anything from atoms to hydrocarbons, and not just, ground state species, but also vibrationally and electronically excited species and plasmas and very high temperature gases. There's a general trend for us to move to both longer wavelengths in the mid-infrared and far-infrared and even terahertz regime, and also to go to shorter wavelengths where we really haven't had access to light sources that are extremely well suited for these types of diagnostics, which is kind of funny because every other diagnostic out there has really been benefiting from the lasers available in that regime for a long time. More extreme conditions. These applications are pushing us to resolve very extreme environments. Things behind high Mach shocks approaching 10,000 Kelvin, where the gas, is really ionized. And then, of course, in things like rockets, we're trying to make measurements at pressures of hundreds of bar. So really extreme conditions where really your only hope to characterize them is with optical techniques. And to make life especially interesting, we often have to deal with every combination thereof. We rarely get to just pick one of these to advance. We often have to advance several combinations simultaneously. Okay, so now I'm going to go into this nitty-gritty on these diagnostics for fireballs and begin with a high-level overview of what's motivating this. We really need high-speed measurements of temperature and species to characterize just the thermochemical evolution of energetic materials and really post-detonation events. Whether it's small-scale explosions or large-scale explosions in the field, we really need diagnostics to characterize both to determine what has happened. We need to measure temperature to monitor energy release and what we call the thermal kill mechanism for bioagents. For example, in our work with DITRA, they're developing energetics that have counter weapon of mass destruction properties and that are designed to destroy stockpiles of bioweapons and chem weapons. So temperature is very important for that. We also need to measure a wide variety of species, not only to understand fireball chemistry, but also the chemical kill mechanism. Some of these explosives contain iodine, which is added to kill anthrax, and therefore understanding how iodine alters fireball chemistry is very important in those scenarios. More generally, we need these measurements to validate fireball models and understand the radiative signature coming from explosive events. And what do I mean by that is there's literally satellites circling the Earth with spectrometers and looking for these types of events. And by monitoring basically the optical signature coming from, say, a large-scale explosion, there's potential to determine not only what type of explosive was used, but also who manufactured it and who used it. So lots of security and counterterrorism interest in getting that predictive capability. What are our challenges? Well, we need to resolve timescales below a microsecond all the way out to a second at times. We need to overcome large optical losses and intense luminosity and just generally a very harsh environment. And that may require fiber coupling and or large standoff distances, which just makes it harder to make these measurements, particularly in these field scale tests I'm showing down there on the right. So I want to take a moment to cover the basics of absorption spectroscopy, and everything in this talk, and I believe Mitchell's is going to be dealing with infrared absorption. In that case, we interrogate molecules that are in different vibrational and rotational states. So these molecules can vibrate and rotate at discrete frequencies, which means that their vibrational and rotational energy is quantized, meaning only certain discrete values are allowed. So we can imagine a water molecule existing in some vibrational energy level here or here, but not in between. And its rotational energy kind of fills in the gaps there. And if that molecular motion leads to an oscillating dipole moment, then when we send in a photon that has an energy and frequency that's equal to the spacing between any two allowed low vibrational states, those photons could be absorbed. And basically, the molecule would move from one level to the next, but what we really care about is just how many photons were absorbed. So we can measure that and may see something like that. If we chose a slightly different frequency to move molecules between two different energy levels, we may see less light is absorbed. And the amount of light that's absorbed is dictated by that fractional population of water molecules, in this case, in each lower state. In reality, those are not fully discrete. There's a variety of broadening mechanisms, say molecular collisions introduce uncertainty in these energy levels, and so they're a bit fuzzy, and the molecules can absorb light over a range of colors according to something that looks a bit like a Gaussian distribution, but nothing we can't model. So the rub is basically this, that molecules can absorb photons with specific energy and frequency. The amount of light that's absorbed depends on thermodynamic conditions. And as engineers, if we measure that, the amount of light that's absorbed at different frequencies, we can back out and infer those conditions, temperature, pressure, mole fraction, and even velocity. Okay, so now I'm going to get into this, what I call tale of two diagnostics that are both on this quest for acquiring high bandwidth laser absorption measurements. And I chose the word bandwidth there because I'm going to use it to describe not only measurement bandwidth, but also spectral bandwidth. And the first one shown here on the left is this tunable diode laser absorption spectroscopy diagnostic using wavelength modulation spectroscopy. The basic idea is we take light from two diode lasers or even three, and they're fiber coupled. These are using telecom optics. And we combine them onto a single fiber, route that light through test gas onto potentially another fiber or straight onto a detector, and then record that signal with a high-speed DAC. Now, unfortunately, it's not as simple as that. We have to resolve how the colors are absorbed in wavelength space. And so we, in this technique, we actually send each laser two waveforms, one to scan the nominal frequency of the laser, in this case at a blazing 500 kilohertz, and then to also modulate the instantaneous wavelength on top of that at an even faster rate of about 50 megahertz. And that is used to really encode the absorption signal in different frequencies that we can extract with lock-in filters. So these are continuous wave light sources. They continually are spitting out photons with the frequencies changing in time. They're narrow band, meaning they only cover a very small region of the electromagnetic spectrum. We're using near-infrared wavelengths to utilize telecom hardware. And with that, we can measure temperature, water, and iodine, and a few other species quite well with lasers that are about the size of a quarter. And with this technique, which was really the goal of it, was we were able to get to microsecond time resolution with 1 megahertz measurement rates, which is about 10 times faster than we've been able to do previously with this exact technique. This is applicable to the lab and the field. You can see here, this is pretty much rack mountable electronics, and it's fiber coupled so we can route light to and from harsh test environments. And unfortunately, because we're using these shorter wavelengths, we're forced with resolving small absorbances. About 1% of the light will be absorbed by the molecules we care about, maybe less. And put that in context, maybe 70 or 80% of the light, or even more, will be extinguished through particulate scattering. So to resolve that small signal that we care about, we have to use this WMS technique. Now, in contrast, I'm going to talk about this ultra-fast laser absorption diagnostic. It uses a light source that takes up the bulk of an optical table, and for good reason. This light source can basically cover the electromagnetic spectrum from the ultraviolet all the way out to the far infrared. And it produces ultra-short femtosecond pulses. And those pulses are spectrally broad. So short in the time domain, broad in the frequency domain. They're essentially each a little mini rainbow that we can tune around in the electromagnetic spectrum. And as we send those pulses through a test gas, different molecules will absorb different colors, and we resolve all that with a spectrograph. So it's a pulse technique, and it's broadband. We're looking at tens of wave numbers, but each pulse produces hundreds of wave numbers of spectral content. We're using mid-infrared colors for this one to measure temperature, CO, NO, and water. And because we're using ultra-short pulses and acquiring single-shot measurements, each measurement is ultra-fast. Each measurement is done in about 10 picoseconds or less. That's set by the time of flight of the pulse through the gas. The rep rate, on the other hand, is modest at 5 kilohertz, but that's still pretty fast. This is applicable to lab for now with fiber coupling and other tricks. We could probably get into a variety of different fields. Using mid-infrared wavelengths, we get much stronger absorbance, anywhere from 0.1 to 1, which means about 60% of the light's absorbed. This is the exponential nature of this. And with those larger signals, we can just use direct absorption spectroscopy. Okay, so without further ado, I'm going to now do a deeper dive on the WMS technique. I said already, we send these lasers two waveforms, one to tune the nominal wavelength and one to tune the instantaneous wavelength. The same thing happens to the intensity of the light exiting the laser. So if you look at a photodetector, you see the intensity of the light following this scan envelope and then this higher frequency modulation envelope. That light goes through an absorbing gas. All the colors in that beam are absorbed according to Beer's law in the absorption spectra of the molecules in this gas. And that's resolved with high fidelity with a really high speed detector and DAC. Now, if you could look at the frequency content of the electric field, not the intensity, but the electric field, what you would see is actually something that resembles that of a frequency cone. And it would consist of discrete frequencies, we call those teeth, that are all spaced apart from one another at a spacing set by that modulation frequency. So optically speaking, 50 megahertz is actually quite small. So this is a really densely packed comb. And really that comb is being scanned back and forth with respect to the absorption lines of the molecule. And then what happens is each tooth is absorbed a different amount. It's also dispersed in the time domain. And what that causes is essentially these teeth to become unbalanced. And so they start beating against each other, and they introduce beat signals at the harmonics of the modulation frequency, which we can actually pick out by, without seeing this directly, we can pick that out from the electrical signal produced by the detector. We can extract these 1F and 2F signals, use our calibration-free WMS models, which we develop ourselves to infer this underlying absorption spectra. Once we have that, it's kind of business as usual to get temperature and mole fraction from those signals. This is a calibration-free technique. 2 colors gets you temperature, 1 color after that gives you mole fraction. And as I said, we use this to improve SNR. We've shown it gives you about a factor of 10 to 100 boost in SNR depending on the environment due to this high frequency modulation combined with lock-in detection and 1F normalization, which basically cancels out non-absorbing intensity losses. So what does it look like in practice? We have, in this case, 3 diode lasers. They're all fiber coupled. They're combined together onto a single fiber. The light from all 3 lasers shoots across the test gas in our high pressure combustion chamber onto a detector, which we then record that signal at high speed using a really high speed DAC, so about 3 gigasamples a second. I've told you about how we process the data already. How do we actually get this stuff to work in practice? We have a series of function generators that are basically locked together on the same clock. The slow scan waveform is at the same frequency for all lasers. It goes right to the controller. The high frequency modulation is at a unique frequency, and it goes straight into the bias T of each laser. And the reason for that is by using different modulation frequencies, either 35, 45.5, or 61.5 megahertz, we essentially encode the absorption signal occurring on any one of those 3 colors at a unique frequency in the Fourier domain. So even though all the laser light is hitting the detector at the same time, by using lock-in filters to pick out the harmonics belonging to a specific laser, we can determine what happened to each color. And that's really the basic for doing this multicolor absorption technique. All right, how about some results? What do these tests look like? We basically create a test charge of HMX with microaluminum. We light off with an E-match. It'll produce a pretty violent deflagration filling our combustion chamber. And after a little bit of time, you'll start to see the micron aluminum particles start to burn. You'll see these aluminum smoke trails kind of trail off of them like fingers. And so it's not a detonation, but still a pretty energetic combustion event. If we look at some measurements, these are 100 kilohertz measurements of temperature, water, and iodine in a case where we actually had molecular iodine crystals mixed into the test sample. And red is temperature, green is iodine, and blue is water. And we can see that we can resolve, we have more than enough measurement bandwidth to resolve all the dynamics of interest in this system. If we look at the iodine signature, we see it's much more temperature sensitive than water. And the reason for that is basically as the temperature shoots up, it can cause not only the iodine crystals to vaporize, but then the iodine to dissociate into atomic iodine, which is what we actually measure. So it tends to be more sensitive. to temperature than water, which is really what's driving the heat release. And then if we look on the back end of things, when the temperature is falling and the iodine's falling and the water is falling because gases are cooling and expanding out of the chamber, we see the iodine fall off faster because as that temperature drops below 2000 K, the atomic iodine is recombining back to I2. So all these species-specific dynamics are really critical to the modelers in the DoD to try and understand the evolution of these blasts and their efficacy at destroying bioweapons. All right, so now I'm going to get into the next part of my talk, which covers this ultra-fast laser absorption diagnostic. How does it work? Very, very differently. Almost could not be more different. We take an ultra-fast high-SAF oscillator running at 80 megahertz. It's putting out pulses centered around 800 nanometers, so in the near infrared. Those pulses go into a regenerative multi-stage amplifier that selectively amplifies pulses at 5 kilohertz, way up in energy to about 2 millijoules per pulse. And that's done really just to drive this wavelength conversion box, which consists of an OPA and a DFG, basically just some crystals in a box. And when the pulses come in at the right angle, we can generate basically any color we want out of those crystals through a variety of nonlinear optical processes. So really an amazing amount of optical science at play, but with the click of a mouse, we change the wavelength coming out of the box. So it's really quite easy in practice, except when it comes out of alignment. Once we pick the color we want coming out, or really where the pulse is centered in wavelength space, we then have to attenuate it a bit in energy. So we use a Rothschild prism polarizer to do that. And once we get the energy level right, we clean up the spatial profile of the beam in a pinhole filter, send the pulse through our test gas, and then spectrally resolve it on a high-speed mid-infrared spectrometer. And basically that camera is taking pictures of the spectral content in each pulse. And if we look at a given row of intensity on each image, it'll show us basically the intensity of light as a wavelength. And the blue shows what it's like without absorbing gas. The red shows what it's like with absorbing gas. And we see these additional dips which come from absorption lines of carbon monoxide. And we can then calculate that absorbance spectra using Beer's law to get this much cleaner looking absorption spectra if we've normalized out all these intensity fluctuations in the beam. And from doing fitting our spectroscopic model to that data, we get temperature, mole fraction. We could even get pressure in some cases. And so we get that data at 5 kilohertz, but remember, each measurement's ultra fast. So everything's done and over with in about 1 to 10 picoseconds. And that's extremely valuable in a highly transient scenario. In this case, we wanted to measure CO, NO, and water simultaneously because they are 3 of the most important combustion products for nitramine combustion, HMX being a nitramine. To do that, we need to use wavelengths centered around 5.1 microns, so on the mid-IR in your 1950 wave numbers, where the absorption bands of all 3 of these molecules intersect. And they're really on the edge of all 3 of these bands. So we get very high energy, lower state transitions in this region, which is advantageous for these high temperature measurements. And we see regions where there's some overlap in the spectra between molecules, but other regions where the absorption lines of a given species are very well isolated. And even after resolving that with our imaging spectrometer, we still get very discrete absorption features that belong to a specific species in a specific quantum state. And so our spectral fitting routine has no problem determining the mole fraction of all 3 of those species and the temperature of those species. I'll say one other thing, because we're looking at a wide range of states and energy levels, we can actually assess and to some extent overcome the impact of thermal non-uniformities on our data sets. That's another added benefit of this quasi or broadband technique. Got some results. Here's a single test, time histories for temperature in black, CO in red, water in blue, and NO in green. And we see the peak temperature is about 2700 Kelvin, as it was in previous work that we've done. NO peaks first, followed by water, and then CO. And this is basically consistent with kinetics governing nitramine combustion. That's not surprising. And one thing we see is also interesting is how the CO falls off before all the others. And where does that come from? That comes from oxidation of CO to CO2. And we get ultimately pretty close to complete removal of CO. And how does that happen? Well, it shouldn't happen for a pure HMX case because HMX is fuel rich and CO balanced. But when we generate these fireballs, they eject into an air atmosphere and entrain lots of oxygen into that turbulent fireball. And that's what drives this process. And we can fully resolve the timescale at which that takes place. How about the measurement quality? 1 sigma precisions of a fraction of a percent and 95% confidence intervals of a few percent, which is pretty much competitive with state-of-the-art techniques that we've been developing for decades. So we've been really, really happy to see that. If we add some aluminum, what happens? Gas stays hotter for longer. Why does that happen? Well, those particles take quite a bit of time to burn, as you saw from that video. So we stay hotter for longer, shown here on the right. And if you look at the y-axis here, we generate about twice as much CO compared to water in the aluminized fireball compared to the non-aluminized fireball on the left. And we can see that more clearly by taking the ratio of those two species mole fractions and looking at how they evolve in time. The red is for plain HMX, no aluminum, and then the black is for the aluminized fireball. I think that's about 20% aluminum by weight. Why does that happen? Most basic explanation is that this environment is now more fuel rich. We've added aluminum into the combustion mixture. It's more fuel rich. On top of that, though, aluminum is readily oxidized by CO2. And for the aluminum particles we're using here, which are less than 10 microns nominally in diameter, this is actually one of the dominant oxidation paths, which leads to formation of ALO and CO. So this is not really a surprising result, but being able to resolve it and quantify it is new. Okay, so I think that brings me to the end here. I'll wrap it up with some concluding remarks. What have we done? We've developed 2 very different classes of laser absorption diagnostics for studying these types of environments. One uses telecom grade diode lasers and near gigahertz wavelength modulation to measure temperature, water, and iodine. We can do that at 100 kilohertz, as I've shown, and up to 1 megahertz. I dropped that slide to give Mitch more time. So we can do this up to 1 megahertz if we want. But this employs fiber-coupled telecom hardware, and that's portable and suitable for field tests, which is great. The other one utilized this broadband ultra-fast technique to measure 3 species and temperatures simultaneously. We've shown that by using these broadband pulses with high-res gratings and then careful wavelength selection is really the key to this. We can make these multi-species measurements simultaneously. And that optical setup was key to us getting to the point of getting single-shot measurements, which provide us this ultra-fast time resolution and the ability to resolve transients taking place on sub-nanosecond timescales. And that's not incredibly valuable for the work I showed here today, but for our future projects, looking at detonation environments and high Mach shocks, it'll be very valuable for us. So it's been good to see that here. Last is just thanking all the important folks. DICTRA funded this WMS diagnostic. Jeff Davis is a program manager there. Meetab Birkin funded the development of the ULAS work, and DICTRA supported the Fireball test campaign. And most importantly, I'd like to thank my students, Vishnu Radhakrishna, shown here, Ryan Tansen here, and Garrett Matthews all contributed heavily to this, and really they did all the hard work. So with that, now I guess I'll pass the floor over to Mitch, and then we'll take questions after that. Oh, I stopped sharing.
Thanks, Chris. That was great.
Yeah, thank you.
All right, Mitch, we are ready for you.
All right, I'm unmuted now. You guys got me?
Yes.
Sorry about that. So just wanted to start and thank Chris. Great talk on high-speed combustion diagnostics, and I think he obviously gave some introductory material that's very relevant. We tried to coordinate our talks a little bit, and so we weren't too redundant, but I'm going to be talking about another frontier in laser diagnostics for combustion, which is in quantitative thermochemical imaging of combustion flows. So this is measuring temperature and species in a multi-dimensional domain, and I'll talk about applications relevant to rockets and wildfires. start with an introduction of my group. You can see us here, one of the last times we were able to, I guess, take a picture all together. And in our lab facility at UCLA. We're also, we do experimental combustion research and also in other sort of non-equilibrium gas dynamics, fields. And our expertise is in spectroscopy and sensors. But we've also started to do more work in, I'd say, more applied propulsion device, combustion device development. And we're currently building a facility in Mojave Desert to support some of that work. So quick outline of my talk. After some brief motivation, I'll talk about our approach to imaging, quantitative imaging of temperature and species, which is mid-infrared laser absorption tomography. And I'll detail one application with some depth, which is hybrid rocket combustion analysis as relevant to injector design. And then I'll also talk about one relevant to wildfires, which is toxicant formation relative to combustion of fire-resistant polymers. And the last part of my talk, I'll talk about some methods advancement that we've been doing in developing a new technique called laser absorption imaging, again, for the same purpose of sort of temperature and species. So, as engineers, I guess going maybe to what Tim mentioned in the beginning is I was really attracted to combustion because, I like to tell people and students that this is one of the hardest fields to study, right? It's this a convolution of really multiple disciplines of heat transfer, fluid mechanics, chemistry, and often in a shared spatial or temporal domain. So part of our role as experimentalists doing research is to create laboratory experiments that reproduce or isolate the relevant physics and related to these, more practical applications like rocket engines or larger scale building fires. And there's a need to have experiments like the one shown here, sort of a jet burner that we can do in the lab that has a convolution of a lot of these physics. And there's a lot of folks that are involved in trying to model these kind of systems. But we need quantitative, multidimensional measurements of this flow field, particular thermochemistry, in order to discern the relevant phenomena and also be able to help anchor and advance these models. So I won't go through another introduction of laser absorption spectroscopy, except to say that, this is our approach to imaging is to use the same spectroscopic interaction that Chris introduced. And I'll just kind of show this slide to remind how we are quantitative in temperature and species. So we use temp-tunable semiconductor lasers typically to have a light source which is sent into some gas medium at a particular frequency that's resonant with a molecular transitions or lines, as is shown here in the blue. And we can tune over those lines in time in order to spectrally resolve them. And using the Beer-Lambert law, calculating absorbance spectrum, as is shown here to the right. And if we probe multiple transitions, these transitions will have variable temperature dependence according to the Boltzmann distribution. And so the ratio of the intensities or the areas of those transitions can be directly related to temperature. And so we can measure temperature in a very quantitative way. And if we know temperature, we can then use the intensity of one of these lines to infer a mole fraction of species. And so the challenge, though, is in many of these experiments that we want to study, they have non-uniform flow fields. So we need to be able to reconcile that, which has been, as Chris mentioned, one of these sort of Achilles heels of absorption spectroscopy, laser absorption, because it is a beam path integrated measurement, a line of sight measurement. Now, it turns out that we've sort of figured out how to do this generally for a long time using tomography. And so, X-ray absorption tomography is very well established for imaging in the medical community and fields. And you can produce very high resolution measurements. Probably some of you, including myself, have had CT scans. But there are some unique challenges with imaging combustion flows, right, using this technique. So tomography is less mature for sort of these high temperature, non-equilibrium flows. Obviously, our combustion flow field doesn't want to sit still for 20 or 30 minutes like you might do when you get a CT scan. So it's very dynamic. And so there's speed challenges. The scales associated with reaction zones and flames are very small relative to maybe some of these medical imaging scales. Beam access can be a challenge depending on the flow field of interest. And also in combustion, we're typically doing tomography to solve for at least two parameters, okay, meaning not just density as is usually done in medical imaging, but both density and temperature. And temperature, the absorption often has a very nonlinear dependence on temperature. And so now the math is a bit more complicated. So it's just a less mature than what's done, but it can be done, and there's obviously precedent for that. So I'll kind of describe how we do it in the context of an application that I've been working on with NASA JPL for the past 3 years now. And so there's a general interest in utilizing hybrid rockets. So those that have the propellants in different phases. So typically a fuel is a solid and the oxidizer is a gas or liquid. Okay, because these have some theoretical or conceptual advantages in safety and potentially cost and some operational characteristics as well. But there's been this challenge in that hybrid rockets have pretty consistently had low combustion performance. So, we measure that typically with a C-star efficiency, which we use to describe combustion efficiency in rockets. And so you can see that defined here in the equation to the right. Let me get my laser pointer. Okay, and so we get specific impulse, which is the ultimate performance metric for rocket propulsion. And we can define the combustor by a C-star parameter and the downstream nozzle by thrust coefficient. So we care about this C-star parameter. And so we have, C-star efficiency is what's usually measured. And it's measured through measurements of pressure in the chamber, as well as knowledge of mass flow rate in your throat area. And that's typically a measured C-star experimentally. Okay, but we can also define that in terms of temperature and molecular weight and specific gas ratio and specific heat ratio of the gas rather. And that's usually how we get the ideal C-star, okay, which is defined by chemical equilibrium. Well, measurements of pressure and mass flow rate are pretty, I'll say, aggregate metrics, right? Indirect, while we have these very complex processes happening in a rocket combustor, in particular with a hybrid, where you don't just have sort of axial variation of temperature and species, but also a strong radial variation for a cylindrical fuel grain. And so our goal was to try to measure the thermochemical structure of a hybrid rocket reaction layer through a quantitative, spatially resolved temperature and species in situ. Okay, so here was our sort of target application. So this is a small sat thruster hybrid rocket being developed at JPL, operating with PMMA, polymethyl methacrylic, and gaseous oxygen. Okay, and so we built an experiment in our lab at UCLA that was representative of this thruster, and you can see it to the right here. So we have a vertically oriented rocket test stand with the fuel grain shown here at the top. This whole thing mounted on a translation stage, which lets us move it in relation to our optical path. We have some mid-infrared light sources here for CO, CO2, and water. Okay, being able to probe those different species at their molecular signatures, and you can see an image of this to the right. So there's some challenges. Chris alluded to some of these. Some of the general ones include extreme temperatures, a lot of sooting, which can have negative effects on optical techniques like scattering and steering. There's also very steep spatial gradients in flow field properties. But in this cylindrical fuel grain configuration, the flow is relatively axisymmetric. And so that actually makes the tomography problem quite a bit easier. And so we exploit this flow symmetry to perform, I'll call it MIR LAT. So this is mid-infrared laser absorption tomography from a single view angle or plane. Okay, so I'll kind of walk through that, what that process is like. So this is a top view of our hybrid rocket test rig in the top right of this slide. And you can see that we have a single beam going across. And if you looked at a measurement at some point in time, it would look like what you see on the left here. And we're scanning over two lines. And in this case, it's carbon monoxide. And then we can translate this entire rig, okay, relative to our optics in order to resolve this absorption line area. So if you integrate these lines in the spectral domain, you'll get line areas which relate to the intensity, and that'll be now spatially resolved. And we can use a pretty simple tomographic inversion operator, enable transform, in order to recover what's inside this path length integral, okay, which is very non-uniform, right, which is our absorption coefficient. Okay, so it's integrated absorption coefficient which is radially resolved. And once we have that, we can now go back to our method of looking at the ratio for two lines in order to infer temperature, and then from the absorption coefficient from one line, we can resolve mole fraction. But now we're getting this in a spatially resolved manner. Okay, so you can see temperature and species being resolved here. So we took this further, so I'm going kind of further down the path of application here to ask, can we make sort of use of this method to assess hybrid rocket motor design? So we wanted to test two sort of canonical injector designs, which are shown here. So we have just a single port, very simple design for our gaseous oxygen coming in to this pre-combustion chamber region, where you get a recirculation zone, and then it impinges on this fuel grain. Okay, and then we use an axial showerhead injector design. So there's some difference in the incipient sort of fluid dynamics that are occurring, and we wanted to know, how does that affect the downstream combustion zone? So we wanted to make these measurements resolve not just radially, but at different axial positions. So we did that by testing at different fuel grain lengths, okay, while holding the oxygen mass flow rate and the other geometry constant. So here are some results. So I'm showing the two different injectors and results at different downstream axial locations, okay, in the combustion zone. And so we can see the reaction layer. So these are measurements of temperature. Okay, so the temperature is sort of capturing this reaction layer near the surface. So 0 here in the radial direction is the very middle of our core flow. Okay, and on the outside edge to the right is very close to our fuel grain surface. Okay, and so you see we start with a relatively confined reaction layer of a few millimeters, and it grows as you go downstream. Okay, and so we see a constant sort of temperature rise in the core flow with axial distance. And it also, as a sanity check, we see that this approaches the equilibrium temperature, which we can calculate from CEA, or chemical equilibrium analysis. So we can see that here shown as a reference at the dashed line. Now, interestingly, the showerhead injector, okay, it shows that we reach that equilibrium temperature much sooner, much more quickly, with a more radially uniform distribution. So we're going to dig into that a little bit more. And we can do that by looking at the speciation. So here we have species measurements for CO, CO2, and water. Okay, and you can see we start again with the single port injector, okay, where we have now what appears like a very sort of radial distribution of equivalence ratio. So we're very fuel rich. We have a lot of CO near the fuel surface. And as you go towards this oxidizer core, we start to see more water and CO2. And so if you look over here at a simulation of the species versus equivalence ratio, you see very similar trends to what we see with the single port injector at a given axial position. Okay, but if we look at the showerhead injector, it looks a bit different. Okay, there's not as strong of sort of radial gradients in speciation. And we also see some change in the ordering of the species if you look in the core flow. Okay, and so we see that what appears to be happening is we have much closer to sort of equilibrium values in the core, and we have a change in the OF, or equivalence ratio, as we go downstream, which we expect from increased fuel regression. So what we can do is we make measurements at different axial distances, and we can assemble that into these 2D images of the reaction layer. Okay, so the left is the single port injector, the right is the showerhead. Okay, and we have really for the first time some direct measurements of this hybrid rocket reaction layer that are quantitative. Okay, and so we have the temperature and the speciation shown just below for the two different injector designs. You can now see it's very prominent now that the showerhead injector design is yielding enhanced combustion progress through increased mixing and radial diffusion that's occurring here. But we see that the CO2 yielding to CO as you go further downstream, and it becomes more fuel rich. So one of the nice things, because we're taking this all the way towards the application, which is can I change my rocket motor design to make it yield higher combustion efficiency? And this looks like the injector design could be quite important in that, whereas previously it was thought that maybe that didn't matter so much because it's just a single gaseous or liquid propellant, whereas compared to say liquid biprop, where you're very concerned with mixing of the two propellants coming in. And then, the other thing that we got out of this project, which we thought was really interesting, was if you typically measure a C star with this pressure and mass flow rate, and we talked about sort of getting this temperature and species distributions. But we thought, well, we can use this C star definition for our combustion performance, and now we can define it spatially based on composition, which defines our gamma and our molecular weight, as well as the measured temperature. So we can actually measure a C star parameter and compare it to the maximum C star that we might expect, but now in the sort of a spatial domain. So we can compare the single port and the showerhead injector at different downstream locations using the C star metric, and we can see it here in 2 dimensions. And so we get something much more, around 90% sort of the max C star or theoretical C star measured through the temperature and composition measurements. Okay, so this is a much more granular metric to assess, say, combustion efficiency as opposed to, mass flow rate and pressure. So I wanted to briefly talk about another application that's very analogous, okay, but more relevant to wildfire. So there's an interest in, understanding toxicant formation in the combustion of fire-resistant polymers, particularly wind-blown fires that have forced convection on buildings that are, so we have fire sort of encroaching upon the urban interface, certainly in California. And so there's a desire to build structures that can, prevent the spread of these unwanted fires. But the mechanisms for the combustion of these materials, these fire-resistant building materials, are not very well characterized. And we know that some of them can form toxicants during combustion that are very undesirable and can be sometimes even a greater safety threat to first responders and residents. And so, it's a solid fuel combustion experiment, and we realized doing these hybrid rocket experiments, this was just a really nice canonical experiment with a cylindrical grain to create what is a 2D quantitative image of a reaction layer for solid fuel combustion, exploiting the benefits of tomography with axisymmetric flow. It's really hard when you have a lot of edge effects, say for like a 2D slab experiment, to make a similar type of measurement. So in this case, we used one of our lasers to try to probe one of these toxicant species, which is hydrogen chloride. And we can do that around 3.3 micron. It's shown here. So this is one of the fundamental vibrational bands of hydrogen chloride. And this is just a zoom in on some of the specific transitions that we selected. So we like to measure multiple transitions to try to get at both temperature and species. Let's go. So, similar challenges, but in this case, even heavier sooting, and obviously we have toxic gas emissions, so we have to do this in our fuel. So I'm just showing sort of the end result here very briefly. So we're combusting PVC, which is fire resistant. Okay, it forms these halides. And so we had some interesting results where we did these measurements of HCl and temperature with the radial and axial resolution. And what we can see here is that as the hydrogen chloride increases as you move with oxidizer flow downstream along this fuel grain surface, okay, PVC surface, we actually see a decrease in the temperature, okay, which is interesting. So we get a very high temperature in the beginning and a decrease. And we can understand this by thinking about the role of HCl in combustion as a radical sink. And so here I show just a few reactions that are relevant. So HCl actually scavenges some hydrogen and OH radicals, okay, which are typically used and are typically part of sort of radical chain branching reactions. And so the lack of OH, this is just one of the key reactions, inhibits this conversion of CO to CO2 and also lowers the heat release, which helps extinguish the flame. But at the same time, this reduced oxidation can yield not only lots of HCl with this particular material, but more CO, which is another issue. So there's increased fire toxicity. So we just did this as somewhat preliminary data, and we're still working on this. So it's kind of in the early phases. So the last little bit of my talk here is on methods of advancement. So we have been using, LAT, I'll call it, for laser absorption tomography for several applications, and we find it super useful, but it has some limitations. Okay, so here's our current approach, is where we sort of mechanically translate a beam across a flow field. And this has some obvious limits in our temporal resolution, right? So this is It's very slow. And also the spatial resolution is limited by the beam size. So you can do this fast, and other researchers that do tomography have, by basically fixing all your optics. So your optical setup can have fixed detectors and lines of sight for your laser beam. And you can do very high-speed measurements, really at the same speed you can do the kind of stuff that Chris is talking about. However, because you're going to space your beams out, this is going to hurt your spatial resolution quite a bit. So it's hard to do high resolution measurements. And so our approach is a little different, and we call it laser absorption imaging, where basically we expand our laser beam to be larger than the flow field of interest, and then we replace all the detectors with a high-speed IR camera. So this takes advantage of two advancements in photonics. One, that we can get mid-infrared lasers at high power now, and we can also get IR cameras that operate at high speed. Okay, and so this has a simplified stationary optical setup. It expands the dimensionality. We actually sample not just in the sort of plane of the page, but also into the page. So it's really looking at a volume, a measurement volume here, as opposed to the other techniques. And because we're not, we're expanding the beam, we're no longer limited by the beam size and resolution, but by the camera pixel spacing. So we can get very high spatial resolution measurements. So I'll talk about in the next just 3 or 4 slides the evolution of that. That we've started just 1D measurements, as can be seen here on the bottom, where we're imaging in a 1D array. And so we have absorption here of fuel and intermediate and a product of combustion, so ethane, CO, and CO2. And in the initial case, we actually translated in the second dimension. And so this would be the kind of images that we can produce at very high spatial resolution. Okay, we still need to perform our tomographic reconstruction. In this case, it is also axisymmetric as the hybrid rocket was. And so we can do that pretty easily, and we produce these quantitative measurements of both species and temperature with spatial resolution on the order of 50 micron. We moved then into sampling in 2D. This was a challenge. Chris worked on this with us a bit, and we had a lot of diffraction issues that we had to try to tackle, and we did that different ways. By when you image coherent light, laser light on a camera, you get these diffraction patterns, and we had to do some fairly rigorous post-processing, Fourier analysis and filtering to get rid of that. And once we figured out how to get past that, we could now sample in 2D, let us produce things like this. So here we're taking an image of ethane. So this is in a flame that's oscillating at 200 hertz. We put in something to cause that, and we can make 2D images that are time resolved on the order of 2 kilohertz. Now we're currently working on doing this in 3 dimensions. So now you need not just a single camera angle, but you need multiple angles in order to get at 3-dimensional images. And so you can see the experiment here where we're now sampling at 6 angles, okay, and we're assuming this one is steady state. So if you want to do this time resolved, you need multiple cameras. Okay, and these are the kind of results we can produce by using traditional sort of linear matrix-based tomographic optimizations schemes with regularization constraints. We can produce 3-dimensional images. This is a doublet flame with CO, mole fraction, and temperature in 3 dimensions. But we found that we had a lot of problems with this. One, we had some blurring, and the fewer camera angles you use, the more blurring you would get. We'd also get these non-physical artifacts in the image fields. And we end up with a very large data set, and all those things just made this more difficult problem. And so if we want to use fewer angles, less data to try to get an image, we would often not be able to resolve the peaks or the valleys with this technique. And so we investigated using deep learning, which is very commonly used in imaging applications, in particular in CT type, so tomography type applications. So we looked in the literature and pulled in a deep neural network that we sort of changed for our application, but it was from sort of medical imaging community, and we replaced this inversion operator for the tomography with this deep neural network, which allows us to establish functional relationships that are highly nonlinear and do it in a quite efficient way. And we then needed to have a training set to perform that deep learning inversion, and we did that based on our knowledge of the flow field and how well we could calculate the projection. Okay, and then we used the projected data, which is ultimately what we measure, in order to and what we would expect from initial simulations to effectively create this intermediate inversion operator function, the deep neural network. And we got some good results with this. So I'm going kind of quick. I know we're running out of time. Okay, this is my, I think, next to last slide. So this is just an example of some of our initial results, which we just published in Optics Letters, that show that with 6 angles, we can get much higher and more accurate, much higher resolution and more accurate measurements using the deep learning operator as opposed to traditional linear tomography. And this can be seen here. It's also shown that it was more accurate. So our measurements, even using fewer angles, were more accurate with the deep learning network as opposed to linear tomography approach to the inversion. Okay, so this is a summary. I'm actually just going to skip that one and go straight to the acknowledgments. So I just want to make sure to acknowledge AFOSR, NSF, and NASA, who all supported various parts of what I presented today, and perhaps most importantly, the students. So we had the work that was in the slides that, I tried to cover a lot of ground, obviously, in a short amount of time. And so this was a compilation of a number of students' work in that group, which I show here. And so with that, I just want to thank everybody for attending and be happy to take any questions.
Okay. Good. Well, thanks, guys. So we have about, I guess, 15-ish minutes or so for questions. So tell you what, I'm just trying to view the chat here, I guess. So I guess we have our first question from Maruna. And Chris, I don't know if you can read that, or I can read it. Tell you what, why don't I just read it out loud to everyone? And so Varun is asking, Chris, can you comment on the advantages and limitations of broadband femtosecond pulses as compared to supercontinuum lasers for absorption spectroscopy? And maybe, Chris, if you want to just kind of contextualize that for the non-laser people in the room, what Varun is asking? Sure. So I guess, so using the supercontinuum lasers, people have investigated basically it's a different strategy for using femtosecond pulses to generate broadband measurements of absorption. And the work I've seen is the basic idea is you take an ultra short pulse and you put it through a highly nonlinear optical fiber, and then it stretches all those colors out in the time domain, and to be a really long pulse that you can actually then resolve temporally with a photodetector. And I don't know, that stuff's been around for at least a couple of decades. I want to say Scott Sanders, one of our colleagues, was a real pioneer in doing some of that in combustion. And in contrast, that has some advantages in the sense that you don't need to use a grading spectrometer and a camera to resolve the pulses. I think that's certainly an advantage that we would like to have. On the downside, though, you stretch the pulse out in time so much that you lose that ultra fast time resolution. And the work that I've been most familiar with is some recent work out of Darmstadt, where it's very difficult to accurately model the instrument broadening. So essentially the effect of you getting these packets of colors that are stretched in time that are then hitting your detector kind of in bunches of colors at the same time. So you still have a spectral resolution problem, and predicting it is very difficult to really model that well. And that's compounded by some of the issues with using high pulse reference and needing really high speed electronics, and you get ringing in the detector and all sorts of things like that. So I think ultimately it's much easier for us to do high fidelity modeling of our spectra using a grading spectrometer. We also get to preserve that ultra fast time resolution. And maybe even most importantly, that technique is applicable to a huge portion of the electromagnetic spectrum, right? We're not reliant on eating these nonlinear fibers, which are only available at certain wavelengths. So there's pros and cons to each for sure, but I'm pretty happy with the way ours has turned out and the advantages it offers. But yeah, I'd love to get away from needing to use a camera if I could. So I'm always kind of looking to see what the status of these methods are. Thank you. Any other questions? Maybe I'll throw a question to both of you while we're waiting for other ones. I think, Chris, you were just emphasizing the point about how a lot of what you do utilizes very almost commoditized sources and fiber optics and things like that. Can you just kind of reflect on a little bit about how that space is opening up, or where it's going in terms of what's easily available, in terms of wavelengths and things like that, about just how you're piggybacking on the telecom industry and where the opportunities that might be for the field of combustion? rather than highly specialized systems, expensive systems?
Yeah, so I think this is a good one for Mitch and I both to answer. So, the telecom stuff is, using telecom lasers and fibers and detectors is great because the cost is basically 10 times smaller than using more exotic wavelengths, say longer wavelengths like in the mid-IR. But that's getting better, and I'd ask Mitch to comment on that since he's a real expert in that area. I would say the primary advantage of working in the near infrared is to leverage this really rugged optical hardware, which has benefited from billions of dollars of R&D in the telecom industry. And to be honest, that has been pretty stable. Those advancements were born out of the 90s, as far as I know, and I haven't seen a whole lot of need to do better in that, apart from getting the light sources that can do produce broadband measurements and things like that, which are becoming available on the market. The mid-infrared, I think, is the more exciting side of things in terms of optical development, where we're getting these new semiconductor lasers and fibers. Mitch, if you want to elaborate on that.
Sure, yeah. We're able to do measurements. I'd say one of the keys of being able to access the mid-infrared with some of these tunable semiconductor sources is we can measure these quantities in very small scale flames, because we have enough absorption over millimeter path lengths. Some of the stuff I'm showing, it's only a few millimeters of, which is on the scale of a lot of flame experiments. And so we're just now able to really do, absorption spectroscopy experiments and measurements in those types of lab experiments now, because the light source is becoming available and sort of affordable. Whereas in the past, if you were using the telecom, you can measure water, methane, a couple of species, and the path lengths need to be a bit longer. So you might be looking at jet engine exhaust or something. But now we can actually do pretty good measurements in small scale flames in the lab.
Yeah, I'd just say another huge driver for that, and that's benefited from that need, is these rotating detonation engines, making these measurements in the annulus. We have trying to shoot light across centimeter path lengths, or sub-centimeter paths, where the mid-infrared is extremely valuable there.
Yep. Let me, Professor Karagosian has a question, which I'll read out loud for everyone. And that is, could one or both of you, I'll let you pick on who wants to go first, comment on using these laser measurements for closed loop control or offline feed forward control?
Sure. Yeah, I think that's one of, definitely a frontier that, maybe we didn't mention, but I think it's one that's being enabled by, in terms of being used in, practical systems, by the lowering cost and miniaturization of a lot of these components that we're seeing. And I think there's no reason we can't do it. I think there has been a few sort of one-off studies that I've seen, at least, but very little in that area. And I think it does represent a significant opportunity.
Yeah, just to elaborate on that, I obviously agree with Mitchell on that. I think the other thing is that by, getting some of these light sources and being able to make measurements in the mid-infrared where we have larger signal-to-noise ratios at times, that makes it easier to make high-quality measurements, which you generally need for these control applications. And so it's certainly been done. Our advisor was probably one of the first people to do that, using diode laser sensors for combustor control in the 90s again. And it's just one of these things where it can be done, but it's not easy. And so we're left in this space where we need to make things better, more robust, more precise, more accurate, and improving the sensing technology to achieve all that really makes this all the more practical, I think.
Thanks.
Maybe I should just add that these types of sensors are used in power plants for sort of long time scale control, like combustion tuning. So they have sensors in, as like sort of SIMS type of placements in power plants that are based on this technology, but not in sort of short time scales like you might have for stability or something like that.
Good. So our next question is, for either of you, can you comment on the intrinsic width of the gas absorption spectra for the characteristic vibration mode? for the design using ultra-fast laser, there'll be a trade-off in frequency and time domain, so that limits detection sensitivity. And can you comment on the best temporal detection resolution of your systems that you can achieve?
Oh, well, so I'll start with the easy part, which is the basically characteristic width of these absorption lines. You know, let's say at densities near STP, talking about 0.1 wave numbers. Now, at high pressures, you may not be able to see any well-resolved absorption lines. So you're talking about looking at a chunk of a band, or maybe even an entire band, which would be, depending on temperature, the bands get wider. So depending on temperature, you're talking 300, 400, 500 wave numbers, something like that. So with the ultra-fast laser we're using now, that has a pulse full width half max of about 300 wave numbers. We can use about 2 pulse full width half maxes. So that gets us to 600 wave numbers of spectral content that we can actually detect well. But I think what you're getting at is something that limits measurement sensitivity on much shorter timescales that we haven't examined. So I can't comment on the ultimate limit of resolution of our diagnostic. It's not something we've looked at very closely. For the types of situations we've been dealing with, as I said, it's really limited by the time of flight of the pulse through the gas, which is significantly larger than the pulse duration. So the pulse duration and the time domain may be, by the time we account for dispersion, some stretching of pulses, it may be close to a picosecond or a few hundred femtoseconds. But time of flight through our medium is 10 picoseconds. So it's not something we've thought about. But that's an interesting question.
This may be our last question. I'll let Devesh stop me, but this is a question for Mitchell. Can you comment on the deep learning inversion for your tomographic reconstruction?
Yeah, no, it's definitely challenging. It's a more efficient process, but the challenge with it is you need a training data set that has a reasonable representation of your flow field in order for it to work and be efficient. And so, for the measurements we showed here, we're looking at methane distributions, which is the fuel. So it's pretty well represented by Gaussian distributions. Now, if you get into, say, intermediates like CO, OH, other species, and you get some, we know what some sort of turbulent combustion distributions look like. It's it's not something that's easy to represent, right? So I actually am working on using some CFD simulations as part of my training data set. But I'd say that is the key challenge with using deep learning, because it definitely is as a solver, it's quite efficient. You just need a good sort of inputs to the training in order to get it to work.
Do you do anything where you can sort of customize your basis functions for it so that they're more physics informed?
Oh, absolutely. Yeah, exactly. So we basically, that's what we're trying to do now. So we're trying to do not just use some arbitrary distributions like some Gaussians, but have a sort of physics trained deep neural network. So we have the absorption process, we model that based on the physics, but it's more of the fluid mechanics side that you also need to have that represent the physics, right? So if you do both, then you can, I think, have something that is not just sort of computationally efficient, but actually can allow you to make quantitative measurements in a way that are quite accurate. If you can have some of those physics incorporated, and so we've taken some steps in that direction, but we're not quite there for, say, like turbulent combustion,
okay.
fields.
Right, Devesh, I'm looking at the time.
Yep. All right. Thank you, Mitch and Chris. What we'll do now is we'll just turn off the recording, and you can stay till 5, and people can turn on their video if they want to interact with you. But